first, y'all were asking about this logit smooth accept reject, how to set the smoothing parameter. And I said it was relatively arbitrary, and it is. But what it reminded me afterwards is that that's a great paper topic if someone wants to do this. There has been absolutely no investigation that I know of on what's an effective way to set that smoothing parameter. All that's known is that theoretically you can lower the parameter to make it closer to a 0-1 indicator as sample size gets bigger. But in any particular application, how do you know what level is most appropriate? So that's something that's relatively easy to do. You could just do Monte Carlo studies where you know the real answer and see where it starts performing well, and how if it gets too large, then the smoothing is too much and the estimator doesn't perform well. So that's anytime these issues come up, then generally that's just a good topic, of a paper topic. So this area is filled with these things. On the same front, Grace told me that a new version of MATLAB has been given to the university for testing, and so she wanted to know if any of you wanted to do the testing. I think it would count as your project for the class if you were to translate all of our exercises into MATLAB and see if they work. All of them. That's kind of or we could discuss, other possibilities. Yeah, do that.
Smoothing, like not all, but.
Oh, smooth the. Do yes, half of one problem set. No. It's a MATLAB 6 something or whatever, and part of the problem is you're not. If you get weird answers, you don't know if it's the version. Of course, you could go back to the old version and see or what. But that's the goal: is to test this and see if we want to keep the new version and put it online. So yeah, if you want to do that, why don't you talk to me and we'll see how much of the problem sets to do. It needs to be somewhat challenging. Okay. Now, last time we talked about the GHK simulator, and I described what it was, and I was hoping it comes across relatively simply as a recursive procedure, but just so you don't get bogged down in the notes and you can look at it later, I wrote it up again. This is the same thing I did last time, and so you can go over this, and each time you go through, hopefully it'll be more obvious what exactly is happening. But we can also draw a picture of it. And that's what I want to do now. Draw a picture of how the GHK simulator works. And this gives an intuitive idea for why it works. And then in the rest of the lecture, I want to talk about technical issues on how you actually go about estimation, things that are beyond this particular simulator. Okay, suppose we got a 3 alternative situation. And so, of course, what we're looking at is utility differences to see what the probability is. And let's suppose the person chose alternative 3. We're trying to find out what is the probability for alternative 3. So we're going to subtract alternative 3 from the first 2 alternatives, the representative utility, and then the errors will be for error differences, the first minus the third, and the second minus the third. So essentially, we've got 2 error differences. And we can represent it in 2 dimensions as the errors that we're interested in. So the probability ends up being probability of alternative 3 for person n is the probability that the first error term is less than error difference of the first relative to the third divided by the top left element of the Cholesky factor. Okay, this is just what we had last time. Okay. And then times the probability that the second independent error term is less than minus the second alternative difference, plus C12, that is the element of the Cholesky factor for the second row, times the first random term, divided by C22, given that that occurs, and times etc. Okay. Or actually in 3 dimensions, that's all it is. There are 3 alternatives. So we can represent graphically what this probability actually is, and then graphically see how the GHK simulator approximates it. The first thing we know is that we've got 2 error terms, 2 independent error terms, because we create the correlation through the Cholesky factor. So we've got these 2 independent standard normal deviates. The first one has to be below that. The second one has to be below that. So the first one, we can state this condition very easily. We know that eta 1 has to be below, let's just say that the value is here. That's an observed quantity. You just calculate it. And so we know that the first random standard normal deviate has to be to the left of that. And then we also know that the second one has to meet this criterion. But this criterion depends on epsilon 1. I'm sorry, eta 1. So it's not a straight line. It depends, the cutoff for eta 2 depends on the value of eta 1. But we can draw in a line that represents that. I mean, it is a line, it's not horizontal or vertical. Let's say eta 0, then we know that eta 2 has to be the ratio of these 2. So we know if eta 1 is 0, the cutoff point for eta 2 is negative V23n plus, I'm sorry, there's no plus because that's 0 there, divided by C22. So notice that these 2 intercepts take the same form, the 2 points here where you intercept the axis. Yeah.
Do you think the negative V would be positive?
I'm just doing that because the graph looks better. Otherwise, you get everything crammed down here. It can be on either side. Okay, but then notice that as you increase eta from 1 from 0, then essentially this becomes a negative ratio of these 2 C's times whatever you increase that. So you've got a downward slope. You've got this second criterion being a line that is a downward slope. It does not intersect there. There's no reason it would. And the slope is the ratio of these 2 Cholesky factors elements. What? Where it intersects? It can go either direction. It would be highly coincidental that it's there. But it is downward sloping. It's downward sloping at the ratio of these 2. Okay, so now we know exactly what the probability of alternative 3 is graphically. We know the error for the first eta has to be to the left here, and the second one has to be below here. So what we've got is this area over here is the probability of alternative 3. So what we want, whoops. We want to know of the whole area. You know, these errors can take any value, and the probability of being somewhere here is 1, so it all, in a sense, sums up to 1. And we want to know of that, what portion of it is in this area. That's the probability for alternative 3, where both the errors fall in the right area part. Okay, well, you can think about this as being what share is of the space looked at this way, what share is to the left of this line? That's a particular share. So it's share to the left of the vertical dotted line. Okay. Times of that space that's over here, what share of that is below the other dotted line? Okay. So it's the times the share of that that's below this line. Okay. Well, this is exactly what thinking of it this way is what the GHK simulator does. It first calculates the area to the left of this point. Okay? So the first probability it calculates is exact. It doesn't take any draws. And then it takes a draw of eta 1 within this range. Okay? And for that eta 1, say it's this one, eta 1R, it calculates what share of this is below that line. It then says, okay, given eta 1, what's the probability that eta 2 is below that line? So essentially it's capturing, don't draw this on your graph because it'll just get too complicated. But it's saying, given eta 1, we want to know of this total probability here, what share is below the line. Okay? And then it just does that for repeatedly randomly chosen eta 1s and averages them. So you get eta 1 there, and you get that share. Eta 2 for your second draw. And you get this as a share of the total. And you average those. That gives you the average this. What you're wanting here is what is this as an average of this whole thing, or as a share of the whole thing. So it calculates it at various points and takes the average. Since this is linear, then that average is what you're wanting. So essentially, if you did this for enough points, essentially you're just saying, if you did it for enough draws, you're averaging here, averaging there, and averaging at every single point. But what we're doing is just randomly selecting draws. The randomly selected draws give us an unbiased estimator of what this is, because each one has the correct probability. But it's inaccurate because you're not doing it for every single point. It becomes more accurate the more points you draw. So does this make sense? What's happening? I want to emphasize this. You'll see today and then in the problem set, Probit is extremely hard to deal with. Thinking about the simulator, thinking about the estimation, you'll find that the estimation is hard because it's hard to get convergence a lot of times. Nevertheless, it's worth working through all this because the GHK simulator is extremely good. It's very accurate for a few number of draws. It's better than any other simulator for any other model that I've seen. And so it's worth putting forth the effort. Also, the Probit model in general is just extremely useful. So like I said, I resisted using Probits for a long time because of the complication involved, but it really is worth working through it. So I encourage that. Now, I wanted to talk about in lecture today, but we're not going to have time. So I wanted to show that GHK is an important sampler. So I've got here a demonstration of that in a way that should be relatively straightforward to read now that we've gotten all the notation that we have already. I kind of want to take credit for this stuff because I would like y'all to go back and read the Haja Vasiliou article on this. It's like you wonder whether people are even trying to communicate. So it's taken a lot of time, and I think it's a really nice, concise explanation here that comes across well. Okay, so that kind of finishes up last lecture. Any issues, questions? Okay, now what I want to talk about are issues that are in a sense technical, but can also be conceptual on estimation of Probit models and GHK in particular. There's 3 issues that I want to deal with. One is identification. They all have to do with actual estimation of the model. How do you know your model's identified? This is the same problem we have in econometrics all the time. You got to know your parameters are identified before you can estimate them. How do you know in a Probit model when your model when it's identified? And you'll find this is actually not as straightforward as you might think. Secondly, we have a covariance matrix that we're estimating, and yet we want to assure that it's positive definite. How do we do that from the computer's point of view? The computer won't necessarily give us a positive definite covariance matrix. We've got to do something to assure that that happens. And then third, recall that we were calculating a Cholesky factor for error differences with respect to the chosen alternative. So a person who chose alternative 3, we get their error omega for their error differences with respect to alternative 3. But a person who chooses alternative 2, we calculate their probability based on the Cholesky factor of the omega for error differences against alternative 2. And so we're using different covariance matrices here. But obviously they have to be related because they're both derived from the same underlying covariance matrix for the non-differenced errors, for the original errors. How do we assure in our computer run that we have the same parameters arising in each person's covariance matrix? Okay, so assure that is, the parameters in one person's covariance matrix are necessarily related to the parameters in another person's covariance matrix, though they're not the same because you're taking different error differences. You've got to make sure somehow that occurs. So let's talk about identification first. These two are relatively technical. They really only have to do with estimation, and they're not conceptual. We'll see how to handle them in estimation. Identification is actually a very important conceptual issue. How you think about your model, how you interpret the results, and of course, how you estimate. So it has estimation implications. Okay, so let's write the model out as we stand, and kind of do in a conceptual way the original model in utilities. The utility for person n for alternative I. Get a vector of the errors, which is j long. And the model has, is in a sense defined by the covariance matrix of these, which we're saying is omega. That's our original model. Omega has how many free elements? It's symmetric, and so it has j times j plus 1 divided by 2 elements. So if there's 5 alternatives, then what does that come to? 5 times 6 is 30, 15 elements of your covariance matrix. Okay, what I'm going to argue is that you don't actually have 15 identified parameters. You have considerably fewer identified parameters, and you have to know when you're specifying your omega, you have to assure that you actually don't have too many elements that are free, and that you impose identification of some kind. Okay, so the first reason you don't have 15 free elements is that, as we know, only error differences matter. Only differences in utility make any impact on behavior. So we can actually rewrite this in the way we've done several times already as differences in utility from one alternative to another. The one you're differencing against then gets a utility of 0, and everything else is compared to that. It's a way of essentially setting the level. You set the level of one utility equal to 0, all the rest of them become differences against that 0. So we do that by, let's difference against alternative, where am I? 1. Okay, this is one way to think about it. There's a variety of ways to think about identification, but I find this easiest. Difference against first alternative. You can difference against any of them, but generally, I like doing it on the first one because you will always set up your data where there is a first alternative for a person. If you have a set of alternatives, like 4 mode choices, it could be that some people don't have but 3 options available to them. And so the last alternative doesn't necessarily exist for everyone. The first alternative, you're always going to have something listed first, and so that first alternative is always going to exist. So it's kind of good to do it that way, just from a practical perspective. So anyway, you take these as differences against the first alternative, And you have error differences. The error for the first alternative is 0, and the rest of them are interpreted as relative to that. You get a vector. So 2, 1, n, up to j, 1n. So this is j minus 1 length. You don't do the first one, 0. And then this is normally distributed with a covariance matrix that is derived from this. Yes. Okay. This is the covariance matrix of error differences when you take against the first alternative. It's derived from your overall omega. But the interesting thing is j minus 1, omega 1 is j minus 1 in size. So it has j minus 1 times j divided by 2 elements, symmetric, so that the top half doesn't matter. And so there, if you've got 5 alternatives, what do you got? You got 4 times 5 is 20, 10. So actually you only got 10 free elements after you've taken account for the fact that only error differences matter. So if you tried to parameterize in terms of 15, you would have at least 5 that are unidentified. Okay. There's one more thing though. So this is error differences, only differences matter. We've taken account of that by differencing against the first alternative. The second thing we need to account for is that scale doesn't matter. Scale of utility is arbitrary, as we've discussed several times. You can multiply everything by any scale factor and it doesn't change the behavior. So you need to set the scale in some way. The standard way to set scale is to set the variance of one of the alternatives. Remember we showed very early, I think it was maybe the second lecture, how the variance of the error term relates to the scale of the parameters. You can divide by the standard deviation of the error term, and that's equivalent to normalizing the variance to 1. Okay? So what you're doing is you want to normalize one of the variance terms to 1. So if you have a covariance matrix that is for the error differences, that is S11, S12 on up, and it has like I've said, 10 elements. What you need to do next to account for the fact that that scale doesn't matter is normalize one of the diagonal elements to some number, say 1. Doesn't matter what. I traditionally just take the top left one because it has it helps make your Cholesky factorization easy, as you'll see. So the second thing you need to do is to normalize one of the variances to some number. I often take the top left one and normalize it to 1. And that means you have normalized your omega matrix. That matrix has j minus 1 times j divided by 2 minus 1 free elements. And with 5 alts, that's 9 elements. So you actually have only 9 elements instead of 15. As you can guess here, as the more alternatives you have, the fewer covariance elements are actually free as a share. Okay. So there's 2 things you need to remember. Differences don't matter. That places restrictions on how many covariance parameters you can actually estimate. And scale doesn't matter. So you need to set the scale, which means you lose one of the covariance factors, one of the covariance elements. So now let me be explicit about this, because a lot of times you will want to go through, you know that this is all you can estimate, but your thought process when you're thinking about your model is often in terms of your original errors. You can think about how those errors change and relate to each other. It's harder to think about error differences and how they relate. So often you'll start with your conceptualization here and then derive that. So I want to work through that.
But once we estimate the normalized omega 1, we still can't get the S1 to S21, right? Because what we estimate will be S12 divided by S11,
Yes.
right?
You will, yes.
So
Actually,
can
let
I-
me work through what I'm going to do, and that'll show you it's even worse than what you think. But this is not a restriction. The important thing, I want to get into this later, but you need to know up front, this is not a restriction on your estimation. It's not saying, well, you want to be able to estimate something that you can't. What this is telling is, this is all that exists. There is nothing else out there. You can think in terms of there being 15 elements, but they're not. All that affects behavior is these elements. And you need to be able to make that translation, keep that in mind. It's not like reality is richer than we can estimate. The reality is just as restricted as what we're going to show here. Okay, so suppose we got a 4 alternative situation, and our original omega matrix is S11, S12, S13, S14. I'm going to be very explicit here. Okay. Obviously, these are equal when they're cross. Okay, so we start with this. This is how it's easiest to think about things. As we'll see, that's not identified, and in fact, thinking about it can be misleading rather than helpful.
So is this omega or omega 1?
This is omega. So 4 alternative model is you start with omega. Now we're going to derive omega 1 on unnormalized. What's that going to be? It's 3 by 3 instead of 4 by 4. The first element is, each element here is expectation of epsilon 2 minus epsilon 1 times epsilon 2 minus epsilon 1. That's this element here. So that has that squared plus 2 times covariance. It's S11 plus S22 minus 2 S12. Now we go to this element. I'm going to move this over because I need more space. Yes, S11 squared plus S22 squared. No, these are variances already. Right. Minus 2 S12. Okay, now the second element here is the error difference for the second alternative times the error difference for the third alternative. As you recall, this is 2 minus 1, 3 minus 1, 4 minus 1, 2 minus 1, 3 minus 1, 4 minus 1. So here you get epsilon S11 again, okay, plus S3, S2, no, 3, 1, minus S13 minus S12. Okay. Here you just fill it out. 1, 1 plus S41 minus S14 minus S12. Let's see, 2, 3, right here, right.
Instead of 1, 2.
Let's see, you got a 2, 3 here, a 1, 1 there, a 1, 3, and a 1, 2. So that's right. And then you just follow through the pattern for all the rest of them. Right, okay. And then this element becomes S11 plus S22 minus 2 S1, I'm sorry, threes, S11 plus S44 minus 2 S14. And this becomes 1, 1, 4, 3, 1, 4, 1, 3. And then equal elements over there. So now we've gotten the differences accounted for. Okay? And notice that we've already lost a lot of parameters here, and all we're estimating is conglomerates at this stage. But then it gets even worse. We have to normalize this to 1. So essentially, that's the normalized is equal to dividing everything by that, which is 1, S11 plus S23 minus S13 minus S12 divided by S11 plus S23 minus S13, I'm sorry, divided by this. Okay. And then just continue on for the rest of them. The variance here, the diagonal element. Say, et cetera, et cetera, et cetera. Just like they did. So if you now estimate the elements of omega 1, which is all that you've got identified, you're actually estimating something that is a conglomerate of a lot of variances and covariances. As a result, it becomes extremely hard to interpret this. You can think of this as the correlation between the error differences for alternative 2 versus alternative 3. And that's what it is. And in that sense, it's a very simple parameter. It's just the covariance between those two. But you realize that those covariances themselves don't just tell you how things relate, 2 and 3 relate, because both of those error differences include alternative 1's error. And so the two could be correlated, and in fact have to be correlated. Even if alternative 2 and 3 are not correlated, this will be positive because of the common influence of alternative 1's error term. So you can't interpret this as being necessarily related to the ways in which alternative 2 and 3 are correlated. It could simply reflect the common influence of alternative 1, which is determined by not only its own variance, but by its covariance with alternative 2 and its covariance with alternative 3. So these become extremely difficult to interpret. In your problem, in the exercise on the computer, you'll have a chance to try to interpret these. And as I tell you in that exercise, usually the easiest way to interpret them is to then take the next step and use the estimated model for forecasting. So you can then see what substitution patterns are implied, and that tells you where the correlation patterns have to be, or what the practical implications of all this are. But the first thing to note is that these parameters that you estimate incorporate a lot of information, and ferreting out useful information is difficult. Now, you might think that this means, Probit, that's a problem with Probit, because I can't estimate what I want. I want to find out what this correlation matrix is. This thing here is not a problem with Probit. It's a conceptual problem of behavior. Essentially, it's easy for us to think in these terms, but that's not what behavior is determined by. Behavior is only determined by this. And so the problem here is we find it very hard to think of how the behavior actually occurs, which is through this. And thinking in terms of this as a kind of crutch, it sometimes can be useful, but actually makes you think you might know more than you actually do. So this is the real world is acting this way, not not just the econometrics. Now, why does this arise in Probit and not in logit or nested logit? Because in logit and nested logit, there's so many restrictions on these parameters to start with that the whole thing's identified just by assumption. Essentially, logit, we assume that the diagonal elements have variance pi squared over 6, and the off-diagonal elements are 0. And so if you actually make that assumption, you can go through and interpret each of these. These elements have real meaning because all the off-diagonal elements are 0. These are normalized to some particular number. So it's not that this problem doesn't arise in nested logit and logit, it's just been camouflaged by the assumptions that we have put into the error distribution. We've made so many restrictions there that we're no longer concerned about these things. They're automatic. Okay, now, often to get interpretation out of your covariance matrix that you estimate, you're going to want to put some structure. Here you've got, with 5 alternatives, you've got 9 free elements. That's quite a few. If you had a model with 10 alternatives, you would have too many covariance elements to really want to estimate. I mean, you usually don't want that much information, and your data don't contain that much information. With 10, it would be 9 times 5, which is 45, 44 covariance parameters. Generally, you don't want to do that. You can't get good estimates for them. And secondly, since it doesn't give you a lot of information, unless you're just predicting, you probably don't want to use a full covariance matrix. You want to apply some kind of structure that then allows you to interpret what's going on. And structure essentially means restricting this in some way that you're willing to live with, that you think makes sense for your situation, and yet ends up with parameters that are estimated that are meaningful for you. Right? And yet, when you do that, you need to always keep in mind the identification and make sure that your model is identified. So I'm going to go through an example here of a structured model that looks identified at first glance, but actually isn't. So you want to go through these 2 steps, whatever covariance matrix you start with. So suppose we have our original covariance matrix with 4 alternatives as this. Okay. This seems quite reasonable. You put a lot of structure on this thing already. What you say is that these 2 alternatives have the same variance, these 2 have the same variance, and these 2 are correlated with each other by some amount, and these are correlated with each other by some amount. But that this group and this group are uncorrelated with each other. So you've actually only got 2 variance terms and 2 covariance terms. You've got in total 4 parameters. And if you ask the simple question, is this identified? You'd go to this thing here and say, okay, well, we have this many identified parameters in a covariance matrix. So we've got, with 4 alternatives, 3 times 4 is 12 divided by 2 is 6 minus 1. We've got 5 free parameters. All I'm estimating is 4, so I must be fine. The answer is no, you're not. You actually have a sufficiently low number of parameters, but the way you've specified it is still not identified. We'll work that out. So you really have to work through the identification each time. What is the unnormalized So we're going to now subtract out the first alternative and express the rest as differences with respect to the first. It's 2m minus 2r, which is m plus m minus 2r, m minus r, m minus r, m plus k, it's k plus m minus 2 times the covariance, which is 0, okay. M plus s, and m plus k. And then your normalized version of it after you put the top left element to 1 is 1 m minus r divided by twice that is a half. So this element, as soon as you fix the first one, the covariance element gets fixed also. So this is m plus k divided by 2m minus r, m plus s divided by 2m minus r, and m plus k divided by 2m minus r. So if you look here, you notice you only have 2 separate parameters that are being estimated. This is the same as that, and that's different. So you're estimating 2 parameters. That's all you can estimate. You can't possibly get your 4 elements, m, k, r, and s, from those 2 estimates. Okay? You get some estimate for these 2, and if you're doing this, you'd have to program it such that these 2 elements are constrained to be equal, to have that structure. And then the off-diagonal element. Notice the denominator is the difference between m and r. So all you're really getting at most is a difference between the variance and the covariance. This will often be the case, that you cannot estimate a variance per se, you can only estimate a variance relative to a covariance. We on yet? Okay, ask the question.
So you cannot group the alternatives in pairs when you have an odd number?
The more precise answer is you can't estimate, when you group them in pairs, you can't determine the variance and covariance for every pair. You can only determine the variance and covariance of one pair relative to the other pair.
Yeah, but you destroyed more than that, right? You not only destroyed it.
Well, no, in a sense, we can estimate 2 parameters. So why don't we set m equals 1 and r equals 0. Then we can estimate, this essentially becomes 1 plus k over 2. This is 1 plus s over 2. You can estimate those 2 and retrieve k and s. And what that tells you is how does the variance of these elements compare to the variance of these elements. So k is, if it's 1.2, tells you that it's 20% higher than here. And that the covariance is a certain fixed amount more than this. So if the covariance here is 0.8, that's relative to 0 here. So essentially everything, it's kind of like this is a generalized version of the idea that the constants that you enter, alternative specific constants, all of them are really interpreted as the average utility for one relative to the other one. And in a sense, that's all you get out of variances and covariances too. You don't find the variance of one utility or the covariance between 2 utilities. You find the variance of one utility relative to the variance of something else. The covariance of 2 utilities relative to the covariance of something else. And so it's much harder to think in terms of that, but that is truly all that the world has to offer. That's all that affects behavior, is the relative values of these variances and covariances, not their absolute value. And that's essentially what this is saying. So you can get, under any assumptions you want, or normalizations, they're not assumptions, any normalization of m and r, you can find out what k and s are relative to those. But you can't find out their absolute values. So it's not worthless information, but it just is really important to know how to interpret this. And if you tried to start with this as your estimation thing, your model would converge with, would iterate with never converging.
Well, not only can't you figure out the absolute value, but you'll have a problem with the science sometimes, right? Because if you get the ratio of the covariances is going to be positive, it could be that both covariances are negative or both of them are positive, so you
Right.
can retrieve that.
If you normalize
No,
one to be
there's-
positive, then the other one would need to be positive in relation to it. But yeah,
So you-
I think what you're saying is it's hard.
A little bit to 3.
Hmm?
My question was a little bit to number 3,
Yeah.
but I wanted to ask it now. What if we, instead of taking differences for alternative 1, you take difference for alternative 2, and then I'm sure you get something else. Then you estimate it, and you somehow recover more?
Nope.
Okay.
There's nothing more recoverable. If you take if you take differences with respect to something else, all it means is they're going to enter in a different fashion, and it'll be a different fashion that's consistent with this, and just give you the same information in a different form. You do other normalizations perhaps and get, maybe in that situation it would look normal that, or easy to have these normalized and those not normalized. But this is all the information there is. It doesn't, there ain't no mo. Yeah.
If you start by specifying your restricted covariance structure on the norm omega 1, can you avoid this type of problem? Or is it possible to use it?
If you, what?
Well, you specified a restricted covariance structure on omega
Hmm.
and the implications for norm omega 1. If you start by restricting on norm omega 1 and then somehow look back to
What omega would be necessary.
Omega.
Yes, that's what you do. I will describe practically how you end up estimating them. The difficulty with that is it's easy to think of what structure you want here. It's very difficult to think about what structure you want here. Suppose you wanted suppose you were thinking in this matrix and you say, well, I want these two to be correlated and those two to be correlated. Unless you start there, it's very hard to know how it's going to end out here. So that's the basic problem. Yeah.
You just said that, if you make some basic assumptions on M and R, for example, we can find relative K and S. Well, if we know relative K and S to M and R, why can't we get an absolute value? Because we now know M plus K, right?
Oh, we only know if we set M to 1 and R to 0. We now know that this can be interpreted as 1 plus K over 2, and you derive K from that. But you can't then go back and put that K in here and then find the M that makes it equal, because you'll get 1 and 0.
But if we didn't normalize and instead estimated the unnormalized version, then we also knew M minus R, right? Is it that much of complexity to introduce?
No, what I'm trying to say is that if you tried to estimate with this, with all 4 parameters, the model's not identified. You would have a flat area at the top of the likelihood function, which as you move M and K together, it would not change. So there's no maximizing value for each of these two. You can't, it's kind of like, what's an example in standard regression where you have an unidentified parameter? I'm at a loss, they happen all the time.
Set of dummies that add up to
Yeah,
1.
set of dummies that add up to 1. It's the same thing as that. This is just actually the covariance version of a set of dummies adding up to 1. That the covariances levels are not determined, only relative to each other. So this makes it hard to think about these. And this is a problem that cannot be overemphasized. You always have to think about this with your models. With Probit and any of these general models, when you get past the ones that place so many restrictions that the issue doesn't arise, then this comes up. In fact, David Bunch at UC Davis published a paper in which he identified published Probit models that are not identified. That's an embarrassing list to be on. Often your numerical procedure can think you've reached convergence simply because of error, because of the simulation can create bubbles, little ripples in the flat area of the likelihood function. So you can think you can converged even though the true model is not identified. And that happens. So you got to check this beforehand or else you end up with a model that essentially doesn't make sense, that has no meaning.
So what you're saying is that when we estimate this model using either the omega or the Cholesky factorization of it in the likelihood procedure, we have to set certain elements in terms of other elements. There have to be restrictions that we're making one element be some multiple of some other element.
You have to somehow assure that your parameters are identified, is what I'm saying. In this situation, if you work through here, and this is how you're assuring you're identified, then it's obvious that one way to, if you want to work with this matrix, to attain identification is set this to 1 and that to 0. That's one way to do it. So then you can estimate this. If you didn't go through that exercise and tried to estimate the whole thing, you would have an unidentified model. It might converge, you publish, and then be embarrassed when you go give a job talk. So that's what I'm saying. Now, I am going to, after the break, give you a procedure by which you can always assure that this occurs in your estimation. But it's only one procedure. The more general concept is that you need to make sure it's identified. Beyond that, how you do it is an element of choice. You can decide how to do it in various ways. Often, you want to choose the way that makes it's easiest for you to interpret. Okay, so before the break, I want to go through these next two problems, and then after the break, talk about how we solve them all. We want to assure that the covariance matrix is positive definite. So if we estimate this model, we start out with the covariance, we parameterize in terms of the covariance omega 1 covariance matrix. We have two elements. And so we're estimating this as a parameter, that is the same parameter, and then this. If we use this as our parameterization, this is a parameter, and then that, there's no guarantee that the computer is going to give you back elements that give you a positive definite matrix. It could give you a negative here, it could give you a value that's larger here than these two, in which case it's not a covariance matrix. You need to somehow assure that whatever estimates you get and whatever estimates you pass through in the iteration process to get to the maximum are all positive definite. Okay? Similarly, working here, if you were to work in this matrix, set these to 1 and 0, you'd have k and s as your parameters. You would need to assure that any k and s that comes out of the iteration process gives you a positive definite matrix. Okay, so how do you do that? The way you do it is to work in a Cholesky factor and have the parameters be parameters of the Cholesky factor rather than the original covariance matrix. I'll show you how to do that. It turns out that solving these problems is interrelated. The way you solve this depends on how you're handling identification. The way you do this affects the others. So just the clue here is that you work with the parameters being parameters of the Cholesky factor rather than the covariance matrix. Because any lower triangular matrix multiplied by itself is going to give you a positive definite matrix. So there, it doesn't matter what your estimates are, you'll always have the product being positive definite. Yeah. So then the third thing is, when we're doing GHK in particular, I already mentioned this. A person who chooses the first alternative, you calculate P1 using error differences against 1 and utility differences. And you use this omega matrix for the error differences. For a person that chooses alternative 2, remember, we always want the non-chosen error differences to be negative. So here, this person, we take error differences against alternative 2. And in calculating this utility, we use omega 2, which is the covariance of error differences against alternative 2, and et cetera for all the alternatives that a person might choose. Okay? So for this person, we're using omega 1, this person, we're using omega 2, but we know the parameters of these two have to be related because they're both related to some underlying covariance of errors themselves. We have to somehow assure that our parameters in these two matrices are related to each other and are consistent. Okay? So this places, you look about to give up on Probit. So this gives us three things we need to assure in estimation. We need to assure that the model is identified. We need to assure that the model will always give us a positive definite covariance. And we need to assure that the covariance matrices for all the error differences are consistent with one another. You know? How do we do that? That's what we'll talk about after break. So, how do we take care of all three of these things in your model and make sure that you've got an identified model that you're estimating, that your covariance matrix is positive definite, and your omega sub i's are all related to each other? The first key is to recognize that there's an easy transformation to get from these quantities to these quantities. Okay? Let's define a matrix M sub I, which is the identity matrix J minus 1, how to put this? Let me make it for M 3 with 4 alts first. This is 1, 0, 0, 1, I'm sorry, 0, 1, 0, negative 1, negative 1, negative 1, 0, 0, 1. Okay. So it's j minus 1 by j. It's not equal dimensions. J minus 1 rows, j columns. And the way you create it is a j minus 1 identity matrix with a column of negative 1s in column I. Mi is equal to that. So you start out with a j minus 1 identity matrix. So we were making this one M3. We're making it, we start out with an identity matrix that's 3 alternatives. This is a 4 alternative situation, trying to find M3. Okay? You start out with a j minus 1 identity matrix, so it's 3 by 3. And then we add in the third column a set of, I'm sorry, negative 1s. So now in the third column, we put negative 1, so we just insert that column and then continue. Okay, so we can define that for all of these. It's 1, da-da-da, 1, negative 1, negative 1, negative 1, 1, 1. Okay, where this is the ith column. That's the way to define it in general. Okay. So you can define one of these, an M matrix for each of the alternatives. M1 has the column of 1s at the first point. M2 is here, M3, M4, for each of the alternatives. Yeah?
I'm just not clear on what
M is a matrix that I'm going to show you allows you to transform this into this easily. So now I'm just defining it in a way that's totally arbitrary at this stage and going to show you that it works. So let's create these M matrices that are simply an identity matrix with a column of 1 stuck in the ith column. So you create M3 by having an identity matrix with negative 1s in the third column, M4 with the column of 1s in the fourth column, etc. What that allows us to do is transform our model of this form into a model of this form. And actually, you'll use these in your program when you put your data in as data for each alternative. And you want differences, then you use these to create that. Similarly, we'll see in the covariance matrix. So a way to put this in vector notation, stacked utilities. So let's create a vector of these, which is the stacked alternatives. Un is equal to Vn plus epsilon. So that's simply each of these as a vector of length capital J, which is the stacked utilities. And we want to get this, which is these things stacked by utility, J minus 1 of them. Okay. How do we get that from that? What I maintain is you can use this M matrix. So the difference against alternative I, you multiply each of these by your M matrix. So UIN, difference, is equal to MI times UN. This difference is equal to MI VN, epsilon N, I, the differences, is MI epsilon N. So if you want the differences in your explanatory variables, you just pre-multiply them by this matrix M. And that gives you, notice that this is j times 1, because it's the j utility stacked. This is j minus 1 times j. So the whole thing then becomes j minus 1 times 1. So what this does is essentially take the ith element and subtract it from the other ones. And the important thing here for our calculation or estimation of the omega matrices, this is very important, is that the covariance matrix is equal to mi prime. So if you know omega, you calculate this m for each alternative. Then for any particular person, you get the omega for that person for their error differences against their chosen alternative by pre-multiplying and post-multiplying by m on the original covariance matrix. So just to convince you that this works, let's suppose we have, forget the ends just so we don't have so much arithmetic to do. So, and let's say these are 3 alternatives. Whoops. I'm just writing these vectors explicitly. And omega is equal to S11, S12, S13, S22, S23, S33, and similar elements down here. Okay. Now, let's take the difference with respect to the second alternative. So we're wanting to, this is a person who's chosen the second alternative. To do GHK, we want everything differenced against that second alternative.
Quick question, this is per person, right? Because
Yeah.
UN is J by 1, not J times the number of
Right.
observations.
You do this separately for each person, depending on which they chose, because you're always, for each person, going to take differences against their chosen alternative. Okay. So what we want here is M2. M2 is a matrix that's an identity matrix of J minus 1, so it's a 1 like that, but then with negative 1s put in the second column. So we get J minus 1 by J. Okay. And you'll find that M2 times U, which I maintain is this difference, is, let's just do the matrix multiplication. That's U1 minus U2 and negative U2 plus U3, which is obviously the difference. And you got it. Okay. Covariance matrix, we can show that too. It's just a lot of arithmetic. We want to show that omega 2, which is what we want, equal to M2 times omega times M2 prime. Let's just write that out explicitly. Then in the transpose of that. Okay, I'm not going to do this because it takes several steps to do this, but you just multiply this, get a matrix here, and then multiply it times that to get a matrix, and you will end up with same as that. Right. which is the correct matrix. So you can use these m's as just a device for changing your absolute values into differences. Another advantage of it is if you calculate M2 for this person using this procedure here, you calculate, if you calculate omega 2 using this procedure for a person who chose alternative 2, and then you do the same thing to calculate omega 3, transpose. Okay. Then you know that the parameters of omega 2 and omega 3 are related because they're both coming from the same original omega matrix. So if you start somehow with an omega matrix for the non-error differences, for the original errors, pre and post multiplying by these M matrices, then you know that that's going to guarantee that all of your omega sub i's are consistent with each other. So now, using this, what do? This M is just a, it's a trick. Now, what I'm going to describe is one way for assuring that all of these factors, all of these issues get resolved. There are many other ways, and you should think about using other ways if you have a particular model with a certain kind of structure in which it'd be easier to handle this in some other way. But the way I'm going to describe always works, so if you want to use it, you can. So the first thing you do is you parameterize the model in terms of the Cholesky factor that's j minus 1 by j minus 1. Parameterize in terms of Cholesky factor. J minus 1 and j minus 1. Okay? And in this, set top left element to 1. So what you end up with is the Cholesky factor associated with this is what your original, this is what you start with. This is what your parameters actually are. It's going to look like this. So it's j minus 1. If you've got 4 alternatives, this is the correct dimension. It's 3 by 3. And these are the parameters that you're estimating. So when you have starting values in your likelihood function, your starting values are for these. You iterate on these. That's your primal parameters. They're the Cholesky factor elements of the omega 1, which is difference against the first alternative. I'm just doing that because it's convenient. With the top left element held at 1. So you've got these parameters. Then you have your program create omega as C1, C1 prime. Omega 1, yes, thank you. Okay. This is going to take the form, it's also going to be j minus 1 by j minus 1. And it's going to take some form that looks like, I'm just writing it up here so you'll see where the zeros and the non-zeros are. And I'm doing these as what the 2, 3 means. It's the second minus the first interacted with the third minus the first, because they're all against the first. And these now all are simply functions of these. So after you've specified this multiplication gives you these as absolute numbers. They're not parameters. They're calculated from the parameters through this multiplication. What it does is give you a 3 by 3 matrix for that first omega. Then, actually I want to put this all on one board so we can keep seeing it later. Then what you want to do is add top row of zeros and left column of zeros to get omega. So your omega then will look like this, but with zeros around it. So this is now j minus 1 times j minus 1. You make it j by adding zeros at the top and left. This is equivalent to saying your first alternative, we're going to say has an error that has 0 variance. That's equivalent to subtracting the error for the first alternative from the first, which gives it identically 0 error. And then all the rest of them are done this way. So this is a covariance matrix where one of the elements has no variance. So then this becomes simply these things here. Okay. So now you've got your omega. And then the last step is for each person, or for each alternative, you create the Cholesky factor, or let's say this is the next step, 4, and then we'll have a fifth. So you create error differences for every alternative. So you get the omega for all the alternatives. You already had it for the first one. So in a sense, doing this just recreates what you already had for the first alternative, but it does it for all the other alternatives as well. And then finally, you take the Cholesky of that, Ci such that Ci prime is equal to omega I. So all this in terms of programming steps is relatively straightforward. You start with these as your parameters. You multiply that matrix by itself to get an omega matrix, omega 1. You make it the right dimensions, j, by adding zeros at the top and bottom side. Then you use your m's to create the omega matrix for each set of error differences, omega sub I. And then take the Cholesky of that and use this Cholesky factor in your GHK. Yeah?
Step 4, is there an mi prime on the right side of the omega?
Right.
So if we interpret that first row and first column of zeros as the first alternatives has 0 variance, which is that it's somehow normalized to 0, that you subtract its variance from its variance, then how does our interpretation go for the rest of the stuff?
These then become exactly what they are. Essentially, you're saying, I'm subtracting the first alternative's error from itself, and what's left is 0 exactly. Mm-hmm. And all of these, I'm subtracting the first alternative's error. So then
now
these becomes the covariance matrix for the error differences against the first alternative. Sorry.
So the 1 there will now correspond to the variance of alternative 2 normalized to 1.
This will be the covariance of the variance of alternative 2 plus the variance of alternative 1 minus 2 times their covariance is all normalized to 1. So what you're saying here is your original variance of epsilon 1 plus variance of epsilon 2 minus 2 times the covariance of epsilon 1 and epsilon 2. We're setting all that to 1 by doing this. And essentially what that's saying is we can't distinguish what's causing things to happen here. Is it because this has a high variance, this has a high variance, because this has a low covariance. any of those things could cause this quantity to be high. And not only that, we have to scale the whole thing, so we scale it by 1, which means we're dividing all the other ones by it. This is why it's so hard to interpret. But nevertheless, this does give you what you want. It also points out one thing. This omega matrix is singular. An identified omega matrix for the original errors has to be singular. It's not identified. It can't have full rank. And this kind of just makes it absolutely clear that this is singular. It's positive semi-definite rather than positive definite. But each of the omega sub i's through this transformation is going to be positive definite for any values of these c's. So what this does is 3 things. It assures identification because you're parameterizing in error differences with one element set to 1. It assures that you're positive definite because you're parameterizing in the Cholesky factor, and any numbers here, when multiplied by themselves, will give a positive definite matrix. And it assures that all your omega sub i's are related to each other because they're all derived from the same underlying omega. So it all works in together. One thing I should point out here, setting this to 1 is equivalent to setting this element to 1 because what you've got is 1, 0, 0, a number, a 0, a number, times the transpose of this. And so, chung chung, the top left element is going to be 1 of your covariance matrix. So the other advantage of this is you assure your top left element of this covariance matrix is 1 by having the top left element of your Cholesky factor. These are like all these tricks that give you what you need. Again, all of these are just one way of doing it. You could do these things in a million different ways. And everyone develops their own kind of way of doing it.
So is the strategy here to kind of get to the minimum number of parameters that's specified?
This is actually giving you the maximum numbers of parameters that you can have.
That you can have with it that you properly specify.
Right. Now, you could restrict this further by placing some structure on your overall omega, your large omega, this one here, and then seeing what that implies about these and parameters that way. You'll have a case to do that in your problem set. Okay, questions on this? Issues. So now what I want to do is go over the problem, the exercises, and show you the program that actually does this. So you'll see how we're actually following these steps in the program, where they occur, and then if you want to modify the program in certain ways, you'll know how to go about doing it. So here's the code that does the Probit estimation. Y'all are handing that around. All right, let's see. Oops. Everyone got one?
No.
No? Got missing some up here, so pass some back up. This is really going to come across well in the video. How do you focus this thing? This thing? There. Okay. I've got these so you can see what's happening. First of all, recall that what we're estimating here is for a particular person, n chose I. We're wanting to estimate p sub I n, that's the chosen alternative's probability, which depends on the differences with respect to that alternative and the omega of error differences with respect to that. So a person that chose alternative 1, we want variables differenced against alternative 1 and omega 1. A person that chose alternative 2, we want a difference against the second alternative, omega 2. So what we're doing here is all that. What this does is simply we read in our variables as the variables for each of the alternatives and gives the dependent variables. There's a README file that describes what the variables are. For all you need to know now is there's 4 alternatives and there's just some variables. What this does is for every person, difference their variables against the chosen alternatives variable. So a person who chose alternative 1, you subtract out the alternative 1 variables from all the other ones. And the person who chose alternative 2, you subtract out. So what you now end up with is j minus 1 sets the variables instead of j for the differences. It actually should, but I wrote this subroutine before I created the m's and just left it. So it does the same thing, but it does it stupidly. Here are your entering parameters, your starting values. We got the coefficients of the 5 variables, and then we have the elements of this omega C1, the Cholesky factor of the utility difference against alternative 1. So no matter what the person chose, the thing's parameterized in terms of differences against alternative 1, and then we recreate for each person what their own omega matrix is. So these are these 5 parameters right here. And these are the starting values, and what you're going to do is actually estimate those. Should I tell you honestly? The answer is, with Probit models, convergence is a big problem. It's very hard. I chose these that allow it to converge without too many iterations. Yeah. And it's not just close enough. You'll find if you change these, you can be actually closer, but the path it takes will fall somewhere. It'll get caught in this hole where it can't move. Yes, exactly.
So if we're doing our own model, how are we supposed to find it?
This is a big difficulty that everyone has with these models, and I find it the most frustrating. The time spent actually running the models, everyone talks about, it takes 5 hours to run this thing. That's minimal compared to figuring out the labor time, figuring out why you're not converging when you're not converging. That happens a lot in Probit and in all of these models with complicated likelihood functions. The only advice I can give you is you try different starting values. You start finding that it always moves in this direction. It kind of gets in this neighborhood, then it'll maybe fail. But if you start over here, it continues further and gets to a better likelihood. So let's start over there. You try it. I want to make sure. Anyway, never mind. Ready? What happened, and this is getting kind of far afield from the exercise, but simulation puts bumps in the likelihood. And so you can get, your simulation can look it is actually less well behaved than if you were using the true likelihood function. So that makes convergence harder. The true likelihood function is badly behaved. It's not quadratic, and so it's hard to work with anyway. And putting the bumps makes it hard to converge, but it also can make you think you've converged when you haven't, because you can get to the top of a little bump and you think you've converged. So these are extremely difficult. I think this is the key problem. It's not with simulation anymore. We used to have problems with, how do you simulate these models? Now we figured that out. Now we need to find ways to get the maximum easily. It's very difficult. You'll find this. Change the starting values. Change the draws you take, and you'll find that probably half the time you can't converge. And it's a big issue. This is why I'm so excited about the stuff we're going to talk about late in this semester, where you can actually, instead of finding the maximum of the likelihood, you find the mean of the likelihood through simulation. That's stable. You can't ever fail. It takes a tremendously more number of draws, but again, you trade off your own time looking for the maximum with the computer just sitting there chunking. I'm happy to let it do that. This is a whole new area of econometrics that's Bayesians have been doing, but classicists have not adopted at all, and I think we really need to adopt it. Anyway, that's the big problem. These are the starting values. Say how many repetitions to take, how many draws. You're doing 100. It's probably minimal. GHK is pretty good with 100. When you do other simulators like mixed logic, you need like 1,000. Your 100's maybe enough. You probably want more. This is the seed for your random draws. It takes the draws. Okay. Now, these K things here and the M's that we're going to see are what allow us to do these things. K1 is simply this element up here. So since your parameters are these, we somehow have to give the computer the value of this so we can add it on. Okay? And this is, I hold that in K1. I set it here and then took the square root because you actually could normalize not to 1, but you might want to normalize to 2 or 4 or something like that for other reasons. But yet for the Cholesky factor, you're always wanting the square root of whatever it is. So this will just be 1 for us. What this does is K2 ends up being a matrix which is 1s across the diagonal, 1s below the diagonal, and 0s above. Okay. So it's lower diagonal 1s and 0s above. The reason for this, as you'll see, is when you hold these parameters in a vector form, as we read them in as our starting values, and then as it iterates and holds it in the vector form. When you then use Gauss to expand that into a matrix, it puts the vector on both sides of the diagonal, not just the bottom half. And so when I expand the vector parameters into a matrix, I want to get rid of the top half, so I multiply that matrix by this to zero it out. We'll see where you do that later. But for now, just remember that K2 is a lower diagonal 1s. K3 is a row of zeros. K4, obviously I'll use those to go up here. K4 is a column of zeros. I'm going to use those to go here. So essentially, you start with these in vector form, you add the 1, you expand it to a matrix from a vector, which in Gauss gives it both above and below the diagonal. So then you multiply it by this to get only the below diagonal elements. Then you add this at the top, add that at the side, and that gives you omega. Then you multiply by each of the m's to get the omega for each person. Yes. Good point. Okay, then I create the m's. These m's, you already know what they are, and all this does is create them, and then holds them in vector form. So what you end up with is a matrix MM, each row of which is the elements of M of one of those M matrices. So the first row holds M1, the second row holds M2, third row holds M4. It holds it in vector form, so all the elements of the matrix are just put into a long vector and held in this. That way, for any person who chose alternative 1, I can just pull out MM1 for that person. The person who chose alternative 2, I pull out MM2 for that person, so I can automate the pulling of which of these M matrices to use. So I hold them in that. This does the likelihood, and so all that's done just before you start anything. Create all those preliminary matrices. Then you do the log likelihood, the maximization, and that pulls in your log likelihood function. This transforms your data to be differences, and you only do that once at the very first. We've already done that. But then you do the log likelihood. So the first thing you do is you're reading in your starting values. The first starting values are coefficients. The next starting values are elements of the covariance matrix. So this divides that vector of starting values, or whatever values are being read in, into the coefficients in the covariance matrix. Then you add the 1, this element, to the covariance matrix. Okay? So this is now a vector of covariance elements. You add 1 to the first of it. So now you've got a 1 of these 5 numbers. Then expand is Gauss command for expand this vector into a symmetric matrix. So it does that. And then it multiplies it by K2, which only keeps the lower part of it, and zeroes out the top part. Multiplies it by itself so that you get a, the covariance matrix instead of the Cholesky factor. I keep using the same word omega here because that's where we're heading, is to get the omega, but and to save variables. But this is the Cholesky factor right here, and then we multiply it by itself to get the covariance matrix omega. Then we add the row of zeros and the column of zeros, and that gives us our omega matrix that we're going to work with. And then from then on in, for any particular person, what is this? Oh, here. Then I create the Cholesky factor for each of these for all 4 alternatives. You could do this within the loop that calculates for each person. You find out, okay, which do they choose? Let's get the Cholesky factor for them. But it saves time if you just do it 4 times for the 4 alternatives. And then for any person, you just choose whichever of those Cholesky factors you need for that person. Okay. So essentially, you calculate this one Cholesky factor for C1 for each of the 4 alternatives. And that's what this is doing. It pulls in the correct M matrix. It multiplies that M times the omega. And then it saves it in vector form to a matrix S. And then whenever I want this C, I just pull it in this matrix. Okay? And then everything else is very straightforward after that. All of this is the bookkeeping that needs to be done to keep your parameters straight. That's really the only difficult part that is involved, just kind of keeping up with what's happening there. After that, you just multiply the variables times their coefficients, put them in the right shape, and then read all the information into the GHK subroutine. GHK is then a complete subroutine down by itself, which for any particular person calculates the probability for that person given the differences in representative utility. That is for every alternative except the chosen one, the representative utility of that alternative minus the representative utility of the chosen one. So these are the truncation points in that GHK. This is the Cholesky factor that's relevant to that person. And this is a matrix of error terms, uniform deviates, that you use in the GHK. So you feed those in, and then the GHK calculates the probability and spits it out. So what you might want to do is go through and make sure you understand what's happening in this GHK simulator to make sure that it's doing what that sheet of paper that I handed out will lead you to believe it's doing. This you won't ever have to change. If you do another program, you don't need to change this. This, you just create your data to read into it correctly. So this part you need to understand just so you conceptually know what's happening. This part above it, particularly this rearrangement part, you have to know, because that's where you're going to want to make changes when you change the variables, to change the model. If you're going to put structure in your covariance matrix, you're going to reparameterize this some way to allow that structure. Maybe you'll work with this original omega and make sure that this omega is identified, and so you'll skip these steps and start directly here, with this being an identified omega matrix that you're sure is identified, but that is parameterized here, or maybe even the Cholesky of this, and then go down. So this is the part where you're going to change the model in terms of its variance covariance structure. The GHK itself is independent. You don't need to change it. Yeah.
In the end, there's an A, B. You don't have it in the page. You have the last one.
Oh. These two things here.
The numbers
First of all, you've got two procs down here. One of them does the inverse cumulative normal. You need that for GHK. Remember how you do GHK? To do the truncation, you have to take an inverse cumulative normal. This is a program that does it because Gauss won't do it for you. This is a calculation of a cumulative normal that is consistent with this inverse cumulative normal. Gauss has a cumulative normal function, but since it doesn't have an inverse, you can't make sure the two are consistent with each other. So we wrote our own cumulative normal and inverse of that. They're both approximations. All of these variables here are local variables that are just used within that subroutine, if that's what you're asking, with the A, B, W's and stuff. So those are just local variables that are used to create the inverse cumulative normal or the cumulative normal. This is the one part of GHK that I find bad numerically, hard numerically. Inverse cumulative normal and the cumulative normal, but particularly the inverse cumulative normal, is very susceptible to numerical errors, especially when you're getting very small numbers. You can have this. And I've often wondered the extent to which the problems converging arise because small changes in a term can, because the numerical approximation to the inverse cumulative normal can make jumps. So it could be like you're just jumping back and forth and are never going to converge with their true value because of these numerical problems. I don't know. This is another paper topic that's worth looking into. That's the only difficulty, though. GHK is great because it really concentrates the efforts. By taking these cumulative draws within the neighborhoods that they're supposed to be, it concentrates to the correct part of the distribution. And that's why it ends up being so accurate for relatively low number of draws. When we do mixed logit, we'll see that we're drawing from the whole distribution without concentrating, and as a result, you usually need a lot more draws to get the same degree of accuracy. Okay. A little boggling. Okay, so you got the problem set. Go for it. Let's have it done by next Monday. We'll talk about it and then switch over to mixed logit.
So the coefficients that we get, the C's,
Mm-hmm.
that's the C times 1.